Hello class, this is lesson 2.1. The topic is increasing, decreasing, and piecewise functions. So we will begin with the idea of increasing and decreasing. First, let me draw a graph of a function. I'll do the function in green. Let me draw a better picture. Okay, so here's the function. I'll do some x values in red. Okay. Now let's read this graph from left to right. So if we're looking at it from left to right, then we say this is increasing, right? And we say this is constant when it's the horizontal line. So how do we put this in a more mathematical way? Well, we need to describe the location for when the function is increasing. Right, so if we call this the increasing part of the function, how can we describe the location for which this is increasing? Well, we can do it by talking about the x values that correspond to when the function is increasing. So what I mean by that is we say that this function, let's call it f of x, so the function f is increasing for the x values minus infinity to a, and also from b to infinity in this example. So looking at the picture, this is minus infinity to a. These are the x values from minus infinity to a, and the corresponding function is increasing, right? It's going up. And from b to infinity, the function is increasing. Now we say f is constant for the x values a to b in this example. Right, so for the x values here, the corresponding function is constant. Okay, so that's sort of an intuition of an increasing and a constant function. Let me draw a picture of a decreasing function. And I'll do this in red, say we increase, then we're constant, and then decrease. Okay, let's call this A, this B. So in this example, f is increasing for the x values minus infinity to a. F is constant for the x values a to b. And f is decreasing for b to infinity. Right, so again, we think of this as an increasing slope, this as a decreasing slope. And we need a way to talk about the location for which the function is increasing. So for these x values, that is when the function is increasing. For these x values here, that is when the function is constant. For these x values, is when the function is decreasing. Okay, so that's sort of a graphical intuition of increasing, decreasing. Let me now give you a more mathematical definition. So let's let I be an open interval. And we'll let a, b be inside I with a less than b. Okay. So if f of a is less than f of b, that means the function is increasing. f of b less than f of a. Function is decreasing. F of a equals f of b. Then the function is constant. So let me draw the picture here. So for the increasing, for example, say this is a, this is b, well then this is going to be f of a, f of b, right? So clearly this is smaller than that, right? F of a less than f of b in the increasing case. Okay, what about the decreasing case? Well, function's decreasing here, so let's say this is a, this is b. Now f of a is bigger than f of b. Right, so in the decreasing case we have, sorry I wrote the inequality wrong here, sorry about that. F of b less than. And so in the decreasing case, f of b is the smaller one, right? F of b less than f of a. So we have a less than b. Now f of a bigger than f of b. That is the decreasing case. And obviously the outputs are equal when it's constant. We draw that here in our graph. So I'll do a constant part of the function. So if you plug in, say, x1, you plug in x2, well, the corresponding outputs will be equal. You know, these outputs are equal. Okay, so this is sort of the more rigorous definition of increasing, decreasing. And if that was a little confusing, don't worry too much. You could just think about it how we were thinking about it earlier when, you know, when it's going up, that's increasing. When it's going down, that's decreasing. And when we describe the location for which it's increasing and decreasing, we talk about the corresponding x values. Okay, so I'm now going to do a few examples. So let's look at a graph here. Okay, so we have this graph f of x here in red. Let's find the intervals where f is increasing, constant, and decreasing. Okay, well, let's start with increasing. This is when the function's increasing. So we need to talk about the location for which it's increasing, and we describe that by the x values. So f is increasing for the x values -4 to -2. Now f is constant here where we have this horizontal line, so the corresponding x values are -2 to +2. So f is constant for -2 to +2. And similarly, f is decreasing for the x values 2 to 4. Okay. Let me try one more example. So here we have a function in green. Now notice, well, let me put some x values here. Let's say that's -3, -1, 2, 3. So notice here f is increasing two different times. Here's f increasing, and here f is increasing. So for these x values, f is increasing, and also for these x values, f is increasing. So we say f is increasing for minus infinity to minus 3, right, for these x values, minus infinity to minus 3, or sorry, minus infinity to minus 1. Sorry about that. From minus infinity to minus 1 is when f is increasing. I don't know why I put a 3 on this graph. And then also from 2 to 3 is when the function increases again. So we could write it with a comma separated list. Okay, now let's do f is constant for the x values 3 to infinity. Right, so in this picture, 3 to infinity corresponds to these x values, and the corresponding graph is indeed constant. Lastly, let's list when the function is decreasing. F is decreasing for the following x values, from -1 up to 2, and that's the only time it's decreasing, right? So we have -1 to 2. Okay. Let's now look at an example like this. I'm going to draw a graph here in red. I'm going to give you the point here. Let's say this is -1, 2. And let's say this point is 2, -3. Okay. Now we call this the maximum. That's the minimum. This is the location of the maximum. Here's the location of the minimum. Right, so the language we use is, if this was the function f, we say f has a maximum, or I'll use the language relative maximum. I'll explain what I mean by that shortly. So a relative max value 2, and it occurs at x equals -1. F has a relative minimum value of -3, and that occurs when x equals 2. So that should be pretty straightforward from the picture. This is sort of a maximum in this neighborhood. Right at the top of the mountain is the maximum, and the y value is the max value. The x value is the location of the max value. And sort of at the bottom of this valley, the y value is the minimum value. The x value is the location where you attain the minimum value. And when I use the language relative min and relative max, can be demonstrated by this following picture here. So here we have a relative max. Here we have a relative min. Now we have an absolute maximum. Absolute min. Right, so if we just think of the graph in this small neighborhood, then this is a maximum, right? If we just think of this part of the graph here and ignore everywhere else, then this is a maximum in this little neighborhood of the graph. So that's why we use the word relative maximum. But if we look at the graph as a whole, then there's a bigger mountain here, so that's the absolute max. Similarly, in a small neighborhood, this is a minimum, so relatively speaking this is a minimum, but absolutely speaking this is the bigger minimum. So you may see a little bit of language like that in your homework. And notice if you increase and then decrease, you get a maximum in the middle. If you decrease and then increase, you get a minimum in the middle. Okay, so now I want to change topics a little bit and talk about piecewise functions. So a piecewise function is best demonstrated through an example, so I will just show you a piecewise function and then explain how to understand it. So let's say we have a function x plus 1, but that's only when x is bigger than 0. And then we consider the function 3 when x is less than or equal to 0. So we call this a piecewise function because we break the x-axis into pieces. So on this piece of the x-axis, we consider this corresponding function. On this piece of the x-axis, we consider this function. Right, so I'll draw the x-axis and I'll put this piece in green, I'll put this piece in red. Right, so here's the y-axis, here's the x-axis. Now when x is strictly greater than 0, that's this piece in red. X is less than or equal to 0, piece in red. Sorry, this is green, it's red. I might have said red on accident. So x greater than 0 is this piece in green, x less than 0 is this piece in red, right? So now that we broke the x-axis into pieces, let's consider the functions that we are given. So on the green piece, we consider x plus 1. Right? And that's sort of an mx plus b form. It has a slope of 1, y-intercept of 1. So that's pretty easy to graph, but be careful, because we don't want to graph x plus 1 on this red piece. We only want to graph it on the green piece. Okay, so I'd graph it like this, right, where this is the value 1. Right? If we were to just graph x plus 1 on the entire xy plane, it would look like this, but I'm not graphing it on the entire xy plane. I'm only graphing it on a piece of the xy plane, right, on this green piece. Okay, similarly, I'll graph the constant function 3 on the red piece. Okay, so this is a piecewise function. On the red piece, we consider this function. On the green piece, we consider that function. Right? So this is the graphical interpretation of a piecewise function, and this is the algebraic interpretation of it. So when this is bigger than 0, we consider this function. X is less than or equal to 0, we consider this function here. Okay, so how do we plug into these functions? Well, it's pretty easy. So let's plug in the number, I don't know, 4. So how do we plug in a 4? Well, first you have to think, does 4 belong to this piece or to this piece? Obviously 4 is in the green piece, right? 4 is right here. So since 4 belongs to this green piece, you plug in the 4 to the corresponding function, right? F of 4 is 4 plus 1, right? Just plug in a 4 plus 4 into x there. F of 4 equals 5. Okay, what about f of negative 4? What is f of negative 4? Well, first we have to think, where is negative 4? Negative 4 is here in the red piece. So since negative 4 belongs to this piece, we have to plug into the corresponding function. Well, there's nowhere to plug in the 4 here. It's just the constant function 3, so the only thing we can do here is f of negative 4 is 3. There was nowhere to plug in the negative 4. We just get the constant function 3. So plugging in is pretty easy. You just have to be careful about which function you plug into. Okay. actually, it's not too bad. Really the only difficult thing is graphing these. So, like I said earlier, you know how to graph both of these, but you just got to be careful to only graph it on the corresponding piece. So as long as you're careful about that, these problems should be pretty straightforward. Now let me look at an example like this, where we're given the graph of a piecewise function. So we have some piecewise function like this. Say this is the number -3, this is the number -2, this is 2, this is 5. Let us find the domain of this piecewise function. So recall from our earlier lessons, the domain is the x values for which there is a corresponding y value. So here we just look at the x values for which there is a corresponding y value. So obviously -3 to -2, that's in the domain. So we have a closed polka dot here, and then it's open but then closed here. So -3 is in the domain. -2 is also in the domain because we have this closed polka dot. Notice here though, it's just open polka dots over the x equals 2. So 2 is not in the domain. We only have these open polka dots, which means that's not on the graph. But then for 5, we have this closed polka dot, so 5 is in the domain. So how do we write that? Well, -3 and closed polka dot, so I'll use a square bracket. And we go up to 2, and then we do not include 2, because 2 had an open polka dot. So for these closed polka dots, we can use a square bracket. If there's only open polka dots over an x, we have to jump over that value. And so we can plug in all these numbers, we have to jump over the 2, and then we can plug in these numbers. And then for any other x value, there was no corresponding graph, so they are not in the domain. What is the range of this? Well, the range is the y values, right? Let's look at the y values. Let me put some y values. Let's say that's -1 and this is 4. And this is 1 and this is 2. Okay, so the range is just all the y values. So we go from -1, but then we jump over 1, and then we jump over 2, and then go up to 4. So the range is -1 to 1, but there was an open polka dot for the 1, so we jump over it. There was an open polka dot for the 2, so we jump over the 2, and there was the closed polka dot at the 4. So start here, jump over here, jump over here, stop here. Okay, so that's sort of the idea of piecewise functions. The last thing you will encounter in this section is a few word problems, and so I'll just do some similar problems here. Let's say we have a triangle, and we know this leg of the triangle is, say, 88, 0, 0. And this hypotenuse is some d, and then this is some length h. Okay, say we want to write h as a function of d. Well, how do we do that? That means we want h to equal stuff which is numbers and d's on the right hand side. Okay, so first we could notice by the Pythagorean theorem h squared plus 8,800 squared equals d squared, right? And then we just solve for h, so h squared equals d squared minus 0 squared, and then take the square root. Okay, there we have it. Your homework may want you to do some number crunching here. You could just put that in a calculator. And there's your function. It's a function of d because here we just have constant numbers and d's, so d is sort of the input, h is the output, right? Instead of x and y, we're just using d and h. So try not to be too stubborn with the symbols we use. If we used y equals square root of x squared minus 8,800, is obviously y is a function of x. We are used to that. We just use some different letters here. Okay, I will end this lesson with a problem here similar to your homework, which is sort of difficult. Let's say we have a rectangle where this is the width of the rectangle, and we have a shape in here like that. Okay, so we want to find the area of this shape. It's a rhombus. Okay, and we're given some information here. We're given the perimeter of the rectangle. Perimeter of the rectangle is 40. Okay, and then we are given that these points here at the corners of the shape, the points are at the midpoint of the rectangle. The rectangle sides. Okay. Now let's find the area in red as a function of w. Okay, so we want to find a formula for the area, and the formula will have a w in it. So how do we do that? Well, the area of the rectangle, a rectangle, is width times height. Okay. But we weren't really given any information about the height, right? But what we were given was that the parameter is 40. So therefore 40 equals 2w plus 2h. W is the width, h is the height, right? So this length plus that length plus this plus that, that's what the perimeter is, the length of the border, the length of the boundary. So 2 widths, 2 heights, they must equal 40 because we were told that it equals 40. Okay, so we could use this fact to have a formula for the height. If we solve this, we have 2h equals 2w minus 40. Divide both sides by 2. Get h is w minus 20. Or sorry, oops. I made a mistake there. Sorry about that. We minus the 2w over. I wrote that backwards. We get h. 2h is 40 minus 2w. Sorry about that. And then we divide the 2 over. H is 20 minus w. Okay? So we have a formula for h as a function of w. W here. Okay, so what can we do? Well, what we can do is find the area of the entire rectangle and then minus out these green triangles here. If we get the area of the rectangle and minus out the green triangles, we're left with the area in red. Right, so my idea here is we do area of the rectangle minus area of these triangles. That will equal the area in red. Okay, now remember, an area for a triangle is 1/2 base times height. So here's the base, here's the height. Well, in this particular example, the base is half of W, as we can see from the picture here. 1/2 of W. Right, the points are at the midpoints. And then we cut this height in half, and that will be the height of a triangle. Okay, so the height was 20 minus W. We cut it in half. Okay, so we have 20W minus W squared all over 8. That's the area of the triangle. And from this picture, there are 4 of them, 4 triangles. So we should minus out 4 of the triangles. Okay, so now plugging into this idea, the area of the rectangle was the width times the height. What was the height? 20 minus W. And we minus out 4 of the triangle areas. Okay, that will give us the area in red. So we have 20W minus W squared. Okay, now 4 divided by 8 is 1/2. Okay, so we have 20W minus W squared minus 10 plus 1/2 W squared. Okay, so sorry, there was a W there. Let me go back, I forgot to write a W. So the area of the rectangle was width times height, then we do 4 times the area of the triangles. Okay, width times height was given by this. This was height. Now we do minus. So I forgot to write that W last time, sorry about that. So I'll just hurry and clean this up. We have 20W minus W squared minus 10W plus 1/2 W squared. We'll combine the like terms. 10W minus 1/2 W squared. That is the area in red, and it is a function of W because it's a formula with W's in it. Yeah, so I know it's kind of a difficult problem, and I apologize for the typos I made, but that is how we solve the problem here. Okay, and that's all I have for lesson 2.1. Thank you all for watching.